Okay, is everybody there? Go ahead and put your name down there so I can do the roster. Sorry, I'm late. My days are mixed up a little bit. Good morning, Jessica. Let's see here. Where's my book? I'll be right back. Good to see you guys. Got this light coming down right in my eyes. Hope you don't mind. Let's see here. Okay, today's the 14th. All right. Cody, you're here. And Jalen, you're here. Asada, thank you for calling. I was thinking it was Wednesday morning. It's tough being a human. Hello, Mallory. Okay. And Jessica and Millette. Good morning, Joyce. Okay, Jerkita's here. Good morning, Jerkita. Victoria, good morning. Rhonda, good morning to you. Okay, Alexis, good morning. And Haley's here. Good morning, Haley. Caitlin, good morning. And Amanda, Tiffany, good morning. Kia, good morning. How's the audio coming through today? Hopefully no buffering and no skipping. You know, we actually had that happen yesterday afternoon. What a joy that was. I guess all of you can hear since you've responded. Let's see. Didn't I see? Nabi, yep. And Rhonda, I got Cody. Boy, isn't that nice, Landrea? It's clear. What a joy. Okay, Teresa. Okay, Brandy's not there. And Haley and Riley is not there. Let's see if I missed that. Ah, Riley's here. Okay, good. Okay. Okay, Hannah's not here. I don't see her. And Breeley is not here. And Chantel. Okay. Now, we were in the nervous system. Let me shut this door so it won't bother my wife. Yeah, we had a real nice Easter Sunday. Except my wife's got some kind of jaw infection or something going on. Anyway, they got her on an antibiotic for it. So she's resting, so I don't want to disturb her. Let's see. Okay, the last thing we were talking about, we were in chapter 11, weren't we, I believe? Did we finish chapter 11? There you go, that's a little better. Appreciate that, Tiffany. It's not much fun. She's not really feeling very well. But we're on antibiotic and we'll see how it works. It's been a strange kind of illness that's affecting her. But anyway, what's the last thing we talked about in chapter 11? Good morning, Hannah. Good morning. Okay, Landrea says we talked about the sodium potassium pump, and that was in chapter 11, right? Boy, if it isn't a virus, it's kids or the weather or something else. I hope none of you had any damage done to your home. We prepared for it, and we got some good winds, branches out of the trees, but we didn't get any damage to the home. Okay, 393. 393. Okay, and Jerkita says that we were let me X out of this stick here before I break it off. Okay. Great. Okay. Hang on, Alexis, and we'll see. I think it's going to be next Wednesday. All right. Jerkita says, hey, Brandy. Let's see. Okay, good. That's everybody in section 11. Thank you, Monica. I appreciate that. So, Jerkita says we ended on page 82, and that was about the charge across the membrane, probably. 82. Okay, Joyce is saying we're on 93, and Jerkita says we're on 82. So we finished talking about the sodium-potassium pump, which is a protein, one of those proteins that goes through the membrane, and it pumps sodium out and potassium in. And we talked about that, how it threw three ions of sodium out of the cytosol, and it pulled in 2 ions of potassium into the cytosol. So we have sort of an imbalance of charges. Look on page 80. Let's look on page 82 just to make sure we're covering all the bases. Matter of fact, let's hop back to 79, page 79. So you look down at the bottom of page 79 in the second column. And you see the next to the last paragraph, page 79, second column. And you come down to the next to the last paragraph, says the major primary active transport pump in the body is the antipump, antiport. Don't worry about that term. Pump known as the sodium-potassium pump. So as I said, it pumps out 3 ions of sodium from the cytosol outside of the cell, and it pumps in 2 potassium ions into the cell. So we have somewhat of an imbalance there in terms of ions. So if you look on page 82, that first column, and you see where it says in the first paragraph of it, come to the second line, through passive processes such as facilitated diffusion and active processes. And notice it says in about the 1, 2, 3, 4 lines down, these mechanisms cause ions to have unequal concentrations. If you had equal concentrations, they'd be the same charge on either side of the membrane. But we don't have equal concentrations. It's meant to be like that. And so you see the little picture down below of the phospholipid bilayer, and you see ECF at the left of the phospholipid bilayer right above it. You see it says positive on the outside, and then you cross the membrane, you go into the cytosol, and it's negative. Just a little bit, just enough, so that we can say that the cell is charged. Not a large charge or anything like that. But now let's go on down to this paragraph below it. Below the illustration where you see the positive charge on the outside of the membrane, right next to the membrane, and then you inside see a negative charge just right up next against the membrane. Now look at the next paragraph down. Not the one right that says, note that this charge separation is limited. Well, let's look at that. Note that this charge separation is limited to the area on either side of the plasma membrane. On the whole, and don't get too hung up on this, cytosol and ECF have the same overall charge, but right up against the membrane, right up against the cell membrane, positive on the outside, negative on the inside. And that is due to the sodium-potassium pump. That's that protein. We think of a pump. I think we might have mentioned this. Some of you probably have well water, and you've got a pump that brings that water up from the aquifer, puts it in your tank so you can cook and shower with and so forth. So because there's a little bit of a difference in terms of ions, you see it's positive on the outside and negative on the inside. Positive on the ECF side, negative on the cytosol side. Now come down to the next, the second paragraph from that illustration, and you see it says the separation of charges like the ones we see here, that is known as an electrical potential. We often speak about a student's potential, in other words, their ability to do something. So when we have an electrical potential, we've got some energy possibilities that can do something for us, and it does it all the time. That's why I'm talking. It's working. And that's why you're writing down or flipping pages or actively listening. And so you're using ATP in order to create this potential and use it for your purpose. So you see there where it says the bold print term, electrical potential. This name refers to the fact that an electrical potential is a source of potential energy. We've got just enough energy where we can send an electrical impulse through a nerve, through an axon, through the cell body and so forth. And we can talk, we can think, we can blink our eyes, we can move our hands and so forth as you're doing. Now, you see after it says potential energy, why is there potential energy in separated charges? The answer is simple. An electrical potential is really just an electrical gradient. Now you go back to what we covered at the first of the semester, and a gradient is a difference in charge or concentration of a substance, like we talked about some chemicals like glucose passing through a semipermeable membrane. If you have 20 grams per milliliter outside of a cell, and then you've got 5 grams of glucose inside the cell, you've got a gradient. And if that substance, say glucose, can pass through a membrane, then it will do so, because the tendency is to get to zero where there's an equality on either side of the membrane. In this case, we're talking the same thing, a gradient, but it's an electrical gradient because we're dealing with ions, charged particles, as opposed to other substances that are not really considered ions. So, Come on down underneath this thing that says core principle. See the little box that says core principle? I kind of itch right there on the into my nose. Come down a couple of lines under that little box about core principle gradients. And you see in the second line, the electrical potential found across the plasma membrane of all cells is known as a membrane potential. Rhonda, we're on page 82. Page 82 in the textbook. So you see that bold print term, membrane potential, and you see it says the study of these membrane potentials is called electrophysiology. You can actually record the electricity in the human body. That's what you see when you look at an EKG, or I don't know what they call it, maybe an ECG now, but you can see the P wave and the Q wave and the T wave and so forth. That's the movement of ions in the cardiac muscle. Now, we're not going to get into that today, but come down to the next paragraph. You see it says the value of the membrane potential when a cell is at rest, when it is not stimulated or inhibited by any other factor, is called the resting membrane potential. There are some muscles at this point in your body, probably your lower legs or something like that, where those muscles are charged, those nerves are charged and ready to go, but you're not using them. You're using the muscles in your abdomen, you're using the muscles in your back and your shoulders and your hands in order to keep yourself erect, and you use your hand to make notes, to underline some things in the textbook, make some notes about a resting membrane potential. So there are parts of our body that are resting. Jalen, I have no idea what page for the other book. If anybody's using a different book and they're on a different page, that's great. If you would tell Jalen that, because I sure don't know where it is. Now notice, somebody's got the other book. Make sure you give a number. Okay, Joyce, 83. Okay, great. Thank you, Joyce. Appreciate that. Did you get that, Jalen? 83. Okay. Now notice it says resting membrane potential in bold print. And you see the next sentence, the resting membrane potential of most excitable cells. And we're gonna deal with this just in terms of a neuron, which means that their cytosol is 70 millivolts more negative on the inside. 70 millivolts. Sometimes it's 75, some could be 80. It varies a little bit, but 70 is a nice round number. What it's saying is when you can measure that 70 millivolts is that you have a charge across that membrane, a difference in ions, a difference in ions. More positive on the outside, less positive on the inside. So they designate it as actually negative, but it's kind of like less positive. But there's a difference in the charge, in the ions, and therefore you have a charge. You and I have an automobile. We have a car, and you know it can't run without a battery. Battery is used really just to play your radio. It's used to start your car, and you have an alternator that actually generates current for the spark plugs to fire. But your battery is charged. Got some difference of charges there. They talk about 12 volts, don't they? And so if there is no difference in charges, your battery's dead, which means if our cells are not charged, we are dead. Can't do anything with that. All right, so you got those terms, right? And you know how the charges come to be unequal. That's because of the sodium-potassium pump. The pump pumps out 3 sodiums out, pumps in to potassium. So think about the difference in the charge. That's what we need, is just a little difference to have a charge across the membrane. Now let's go over to page 393. That's right, Mallory. That's right. You can measure that. You can put a meter on it. You can see a little hand go up, broop, 12, 12 and a half, 13 volts. That's good. So your battery's charged and it's ready to get you somewhere. So let's go to 393. So on page 393, you're looking in the second column, and you see about a third of the way down, you see that bold print title says Principles of Electrophysiology. Now, outside electrophysiology, I want you to write down 3 things. They all mean the same thing. It's just different ways of people saying basically the same thing. I want you to write down action potential, nerve impulse, and electrochemical signal. Or you could even put message. Some people will call that movement of ions a message. You'll just hear it said like that. It's just one of those things where you got this event and different people use different terms to describe that event. And before we get into looking at the charge on a neuron, I want you to go back to page 354. Go back to page 354. You're going to be looking at figure 1014. Now, we have already gone over this. We've already talked about the events that occur when a muscle contracts, or when a muscle fiber contracts, or a sarcomere shortens. But as you look on page 354, figure 1014, now for Jalen, it might be different. Joyce, if you find it, put that number out forward so those like Jalen can look in their textbook also. Just trying to get you to understand. Thanks, Joyce. 352, Jalen. Appreciate that. Now, as you look at page either 352, for you guys have got a different book, 354 for the other ones, you see the axon terminal. You see the vesicles inside that contain the neurotransmitter acetylcholine. And when it's released, you see the little diamonds coming out through exocytosis. Remember, these are all great questions for tests, right? And you see those little diamonds coming out, and they hook to those purple boxes. Those purple boxes are some kind of gate that opens up when acetylcholine attaches to it. And you see sodium coming in. Now, when that sodium rushes in, that is the start of an action potential, of a nerve impulse. of an electrochemical signal. They're all the same thing, but it's all the movement of ions, in this case, sodium and potassium ions. But it just shows you the sodium. So as you see the sodium come in, now remember, before we go thinking about this, remember before anything happens, it's positive on the outside, negative on the inside. We're talking about the sarcolemma at this point, because we're looking at a picture of a muscle and the nerve and so forth. And so the sodium rushes in, and if you look a little bit to the right, follow the green line, that's the sarcolemma, then you see positive on the inside and negative on the outside, don't you? That changing of the charge is the action potential. That's like when you switch your key on in your car and power flows to your starter, and that starts turning the flywheel in your car, in your engine, and bing, next thing you know, it's up and running. And you can you let off on the key, and you've got an alternator on there that's sending electricity to your spark plug so that they can explode the gasoline and push your car forward. Anyway, you see the inside is becoming positive, and keep going to the right, and you see all those sodium ions coming in. Notice the word right above the big arrow outside the green sarcolemma. It says action potential. Same thing as a nerve impulse. Same thing as an electrical chemical signal. And they may have some other things that I don't know about, but we can deal with it, whatever it is. It's all the same thing. It's a reversal of charge. But you got to have it charged in the first place to have created that message. So the nerve or the muscle has to be charged, positive on the outside, negative on the inside, in order for the reversal of charge to occur, which we call the action potential or the nerve impulse. Now follow those little, go along the sarcolemma, follow those little positive ions. That's positive on the inside now. It's going down the T-tubule, and when it gets out, when it gets to the certain part of the T-tubule, you see it causes the terminal cisternae to open up and calcium ions come out. Now, you already know that. We've already been over that, because the calcium then has to connect to the troponin. Troponin changes shape, and that causes the shape of the tropomyosin. You know that. We've already gone through that. Okay, you got that little bit of a picture? So let's go back to page 393. We're just dealing now with nerves. We were looking at the muscle there, but look on 393, or what did you say it was, Joyce? Let's see, Jerkita, do they work simultaneously? Just about, Jerkita, they do. You know, it's a flash, just like that, just like lightning can hit you and bang, you know, you're hit, or your house is hit or something like that. You know how we've all experienced seeing that lightning come down in just a split second. The same thing happens in the nerve and through the muscle, so that that message is there in, I'm going to guess here, like a tenth of a second, maybe even faster than that, 20th of a second or something like that. But they work together. It's not simultaneously, but it's a step like, where are my fingers? I can't find them on there. But anyway, it's a step-like procedure. They show it in illustration. It looks like, gosh, it ought to take 2 minutes to get down there. No, extremely fast. Think about the athletes who can move their legs so fast. Think about somebody who's taken taekwondo or whatever, and their hands are so fast. They can hit 3 times in the space of a second. It's amazing. It's amazing. And think about our thoughts, how fast they can go through our head. Sometimes they get to our mouth before we check them out and make sure that the thought is right. But it's in a split second. So on 393, we're under that principles of electrophysiology. Now look down to the bottom, and you see this heading called ion channels and gradients. We're not going to get into that. I just want you to be aware there's a lot more than what I'm going to teach you. But you've got these proteins, and you know proteins get made by protein synthesis. And we've got thousands of different proteins in our body. And a number of these proteins are channels that go all the way through the phospholipid bilayer. So you see leak channels. Don't memorize these. I'm not going to ask you about them. Just trying to give you a picture, okay? Gated channels, ligand-gated channels, voltage-gated channels. You see those bold print terms? They're all proteins, and they respond to different chemicals, and they play a role in homeostasis. Now, we're not going to go any farther than that. That's you can get a whole chapter on those channels, and we don't have time for that. So look over on page 394, and you should see a heading that says the resting membrane potential. Now, you see it says we've already discussed the separation of charges. That's what the sodium-potassium pump does. It creates a separation of charges across the plasma membrane. There is a thin layer of negative charges in the cytosol, lining the inside of the membrane, and a thin layer of positive ion charges in the extracellular fluid on the outside of the membrane. This is and there may be other things too, but we're not going to get into that. It gets deep, real deep. So it creates that resting membrane potential. Come on down, recall that this separation is about 1, 2, 3, 4, 5 lines down. Recall that this separation of charges called voltage is simply a type of gradient, ion gradient. It's an ion gradient, referred to as an electrical gradient. Okay, they're just reviewing what we've covered a little bit now. The electrical gradient across the cell membrane is known as the membrane potential, named for the fact that, like any gradient, an electrical gradient is a source of potential energy. It's the change in that gradient that creates the nerve impulse that's going to travel from your brain to your fingers, and you're going to write something, or you're marking it, you're highlighting it, you're bracketing or something like that, so that you know, oh, I got to learn this stuff. Come to the next paragraph, the bottom of the second column, and it says the voltage across the membrane may be measured with a voltmeter, as shown in figure 11.11. You look up at the top of the next page, and you see this picture of the plasma membrane, and you see the positives on the outside and the negatives on the inside. That plasma membrane is charged, just like your battery. And if you come down into the paragraph below that, again, you see the negative voltage, 70 millivolts, and it can vary a little bit, just like our temperatures can vary a little bit. Some of us are 98.6, some of us are 98, some run at 97. That's just the variation, a little bit of leeway in there. The negative voltage is present when the cell is at rest, not being stimulated, not being used in that sense electrically. For this reason, it's called a resting membrane potential. Now, and we've already covered that. The cell is at rest, whether it's a muscle cell or anything else, or an axon. It's not being used. And notice it says the cell is in this state is said to be polarized, which means that the voltage difference across the plasma membrane of the cell is not zero If it's a 0, we're dead. But rather measures to either the positive or the negative side of 0. And you see 70 millivolts down there in the next couple of lines. A typical neuron has a resting membrane potential of minus 70 millivolts. So it's a little less positive on the inside, but we're going to say it's negative on the inside. That's good. And the sodium-potassium pump creates that difference. So in our case, when we're thinking about the neuron, and you remember the book calls the cell membrane of the neuron an axolema. Muscle was a sarcolema, but just for skin cells like this. Of course, these are dead that we're looking at, but other cells in the body, they just call it a cell membrane, phospholipid bilayer. Okay, so we've got this neuron, which is the chapter we're in, looking at neurons. We've got this neuron charged, and the charge is due to the sodium-potassium pump. Probably some other things, but we're not going to get into all of that. Now, I want you to go to page 399. You're looking at figure 1116. Joyce, if you've got sounds like you got a book like Jalen and maybe a couple of other folks. So type in that page if you would. I've got page 399 in my textbook, and we're looking at figure 1116. .402. Thank you, Joyce. So as you look at this picture, look at the number 1, you see the little neuron up there, and they're pointing toward, remember the parts of the neuron, like the dendrites, axon, cell body? See the little block up there? They're talking about the axon hillock. That's from where the axon originates. Now, as you look at the number 1, some sort of stimulus has occurred. For instance, in our case, I'm looking on the screen and I see me. I'd really like to get into Zoom and so I could see you guys. But my eyes see just me. They're picking up the light patterns that come in and they're transferring them to my brain. And of course, I recognize my face because I've been looking at it for 73 years. But you see what's happened is that in the first part of this, where the axolema is, the charge is reversed. That's the action potential. That's the nerve impulse. That's the electrochemical signal that passes eventually to some sort of effector, which would be muscles, could be glands. Some of you have probably experienced being hungry and you walk into your home or a restaurant and you smell one of those flavors. And next thing you know, your mouth's watering. Well, you picked up something in your nasal passage where you have those receptors, and those receptors carried an action potential into your brain. Your brain sends a message down to your salivary glands, your parotid up here, and your sublingual into your tongue, and so forth. And you start producing saliva because you're getting ready to eat, and you want to have it slide down easily. So that's what the purpose of that is. Get some slippery stuff in there so you can get the steak down your throat or the shrimp or whatever. But when this change occurs, remember, it started out positive on the outside, negative on the inside. But when it's stimulated, the sodium starts to rush in. You remember seeing the pictures of the little purple blocks and the sodium was coming through them? And so that process of the ions traversing, crossing the plasma membrane is called depolarization. Now, what I want you to do is draw a line that will come from the area where it's negative on the outside and positive on the inside. Draw a line from there up and write the word depolarization. Remember, this neuron is charged. It's polarized. Now we're going to depolarize it. The movement of ions is depolarization. So right up there by axillema, just draw a little line with an arrow and come up with it and write the word depolarization. Okay, now you got that done. Now you notice it's negative on the outside, positive on the inside, but as you move to your right, you see it's still positive on the outside and negative on the inside. It hasn't depolarized yet. The message has been created at this point, right where you see axillema and the axon hillock up there on the illustration of the neuron. The depolarization is the start of the signal, the electrochemical signal, and it is going to pass all the way down, in this case, the axon, but it's only showing the cell membrane. So you see it's negative on the outside, positive on the inside. Now come to the next illustration below, and that's number 2. Don't worry about voltage-gated sodium channels and all that stuff. We're just going to get the idea. So you see the sodium rushing in. You see it's all positive on the inside. It's moving down. You see it's all negative on the positive on the inside, negative on the outside. So there's a message going down, and all those ions are entering the cell. Those sodium ions are entering the cell, making it positive on the inside, negative on the outside. That's moving down the plasma membrane. And of course, with an axon, that impulse, that electrochemical electrochemical signal moves down the axon, making the outside negative and the inside positive. Now, this happens in a flash. We're taking 10 minutes to talk about it, but it happens in a flash. Come down to the third. All these calls want to come in right when you're in the middle of stuff. Just have to wait. So come down to the third illustration, and you see positive on the outside and negative on the inside. I want you to draw a little arrow to that and write the word repolarization. Repolarization. That is the restoration caused by the sodium-potassium pump of the charge of the resting membrane potential. So you've got the word repolarization. So I'll repeat it, Joyce. And you look above in that number 2, you see all the negatives on the outside and the positives on the inside. So the message, the electrochemical message, is moving down the axon. Well, where that impulse started, where that electrical chemical activity signal started, what you see back now under the third one is you see positive on the outside and negative on the inside. And we're not going to get into all the shifts of the ions, okay? Just know that the sodium-potassium pump and some other things are working to restore the positive charge on the outside and the negative charge on the inside. And that is going to follow the action potential that's traveling to a muscle or a gland, like your salivary glands. So it's like it's discharging and then it's recharged. And Jerkita, you were talking about, does this all happen simultaneously? It is so quick that we have very fluid motions. It's not like jerk, 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 jerk. It's not jerky. It's a very fluid event. Think about the people who, you're doing it every day too. You're just maybe not doing it as an athlete. But think of the Olympics that you watch and the swimmers. And you got all these muscle groups working, the shoulders and doing the breaststroke, and the legs are kicking also in the particular way. So you got a lot of muscles moving, and the kids are moving them as fast as they can because that's going to help them get ahead of the competition. But it happens so quickly, just like with my mouth and my tongue and my breathing. All that has to be coordinated, but impulses are passing and being recharged and pass again and recharge, so that I'm burning up energy. That's one reason we get tired. We burn up the ATP and I don't feel like moving. Or sometimes if you're a teacher, you feel like just shutting your mouth. I don't want to talk for a couple hours. I'm tired. You'd think that wouldn't tire some people out, but it does. So you got depolarization. That's where sodium comes rushing in. You get the gradient takes over. Higher concentration of sodium outside than inside. So you open the gate, in comes the sodium, charge changes, but then you've got the sodium-potassium pump that pumps out that sodium very quickly. You restore that charge, and now it can happen again and again. You got to run away from a dog in your yard. Somebody's dog's gotten out like these pit bulls do, and they try and hurt people, and you're trying to get in that house as fast as you can. Of course, he's trying to do the same thing, and it's happening in his body too. Depolarization, repolarization, depolarization, repolarization. Depolarize means you got a message going down the end of that to that end of that axon. And then you've got sodium potassium reestablishing the resting membrane potential so it can fire again. Feel somewhat comfortable with that? Not sure what you mean, Joyce, by saying, oh, no loading. Can you say that some other way? Okay, Drakita, you're correct. The message has to travel down the nerve, and then it's where the nerve is the axon. Remember the telodendria? It's hooked to the sarcolemma. They don't touch, but that's what they call the neuromuscular junction. But the acetylcholine is released. That causes the gates to open. Sodium rushes in, and literally in just hundredths of a second, that message has been sent, activated the muscle, and the muscle has accomplished what you desired it to be accomplished. Pretty fast, isn't it? I did a little study on, not study, but some research on it. And some of these impulses can go as fast as 200 miles an hour. And of course, they're covering like 3 or 4 feet, aren't they, in a long axon? 200 miles an hour. Joyce, are you okay with what we're saying? I'm not seeing a response to oh no loading or whatever. I'm not sure what you mean there, but you okay with that? Everybody feels somewhat comfortable with the action potential and the repolarization and depolarization? Oh, is that what it is? Thank you, Rhonda. Oh, my. Well, we got what, 57 minutes in before it started messing up. I guess the YouTube and the internet are starting to become somewhat full. I want you to look over on page 403. Joyce, if you know what page that is, where it says conduction speed, there are a couple of columns there, and the first column talks about conduction speed. Thank you, Rhonda. Okay, on page 403, might be 404, 402 in some of your other books, but we're looking at figure 1119. I'm not really going to get into the figure very much, but you want to read about conduction speed, and you see the term saltatory conduction. You come down into the second paragraph under the conduction speed, and you see saltatory conduction. Now, what I want you to understand there is, and this is where you have to go back to your neuron that is myelinated. Remember how the Schwann cell myelinates axons outside of the central nervous system? It myelinates the axons of peripheral nervous system axons. Tell you what, let's go back to the first of that chapter. Let's see. Let's look on page 390. You're looking at figure 11.8. And you notice, as you look at this figure, you've got a cell body, and you got the axon hillock and so forth, and you see the purple stuff around the axon. And you see the internode, which is the section that is myelinated, and you see the breaks, which they call the nodes of Ranvier. What I want you to know is that in these myelinated axons, the message, the electrical activity, occurs at the nodes of Ranvier. And the action potential jumps from node to node. And so that type of travel occurs faster than an unmyelinated nerve can carry. It's not necessarily the easiest thing to understand, but that's what I want you to understand about the nodes of Ranvier. That's where the action takes place in terms of beginning, just at that node. So that insulation helps the neuron fire faster than an unmyelinated neuron can carry a message. That's probably where those 260 mile an hour impulses come from. Okay, just a couple more things. Let's see, where did I see that? Look on page 406. Joyce, if you're there and can discern what's going on, I know Jalen would appreciate it. I don't know where that is in your books, but on page 406, 11.4 is not the figure, but it is the numerical division for sections of information. So if you find 11.4 and it says neuronal synapses, that's where we are. Page 406, neuronal synapses, and then you see in the second column, overview of neuronal synapses. You come down into that paragraph and you see presynaptic and postsynaptic neurons. Presynaptic neurons and postsynaptic neurons. So not only good, thank you, Joyce. Page 405. Presynaptic neuron and postsynaptic neuron. So these neurons can come together. They can meet with each other. And if this is the one that is sending the message from your brain, it may connect with another neuron. And then this neuron carries the message to a muscle or a gland, or what we would generally call an effector. It's going to cause an effect. So this would be a presynaptic neuron. This one would be a postsynaptic neuron. I want you to know that terminology. Same kind of activity goes on in a lot of these connections. Now, one more thing to look at, and I want you to look on page, I want you to go to 11.5. That's the division of the content in the chapter. I've got it on page 413. It may be on page 412 for you guys that have a little different edition. And the last thing we want to cover in this chapter is on page probably page 414. I'm on page 415. We're looking at table 11.3. Table 11.3. We're talking about neurotransmitters. Those are chemicals that are released by the telodendria of one neuron to an effector or maybe to another neuron, the dendrites of another neuron. And so as you look on table 11.3, you see the word major neurotransmitters. We're not going to go memorize all this stuff, just a few of them here. And I want you to highlight acetylcholine. You're already familiar with that. That's what the telodendria release in the neuromuscular junction so that a muscle can begin to contract. So acetylcholine is one neurotransmitter. We have medications that can block neurotransmitters, and that's one reason when you go to the dentist and he puts that needle in the back of your mouth and puts lidocaine, Novocaine, or whatever it might be, it prevents the release of the acetylcholine or whatever neurotransmitter is there. Now, there's several ways that that drug could work. We're not going to get into that, but the point is that you can't get the transmission across. And in our case, in terms of a dentist, we don't feel the pain that would normally be there without that lidocaine or Novocaine. Come down to biogenic amines. These particular ones are made from amino acids. That's why they call them amines. They're made from amino acids. So I want you to check off norepinephrine, epinephrine, dopamine, and serotonin. Any question about those? Okay, so this afternoon, it's what, 11 o'clock, 11:51. Ooh, we're a little bit over, aren't we? Thank you for your patience. I will send you a study guide. So let's plan on having the 4th lecture test next Tuesday. Do you have any questions? Let me look at it, Joyce. I believe you're correct. Nobby, who put you in charge? Is that what are you trying to do? You're correct, Rhonda. Repolarization on 399. Yeah, and picture depolarization occurs in step 1 and step 2. Picture 1 and picture 2. And then when you get to the third one, that's when you see the charges are restored, and that would be repolarization. Well, Nobby, you've started a wave. I hope it doesn't wash you away. We can do it next Thursday if you want to. Okay, now let's see, Lindrea, I'll have to see how to show you that. I do not know how to do that on D2L yet, but I'll make a note and see if I can answer your question there. Okay? All right, folks. You guys have a nice day. Andrea, I'll get back with you as soon as I can. Okay? See you later.